Okay, let's get going here today. So we will finish Chapter 1, start Chapter 2 today. A few announcements. First of all, there was a question last time about how to log on to the computers in this classroom. Here's the login. s-stat-lab. The password is capital H, stat, exclamation mark, exclamation mark. The way I remember the password is Hardin Hall Statistics. I am so very excited. Does anybody need me to repeat this?
Is the stat capitalized?
No, no. You can try if you want to log in. So again, you'll need to eventually log in because it's you're using these computers for the tests. Also, I have contacted our computer support person regarding the, is the line there?
Yes.
It is. Okay. I guess I can't see it. Okay, yeah, I see it. I did contact, I sent him an email about it, and also about the annoying computer that we have in here as well. And I haven't heard back. We shall see if some stuff is done. I hope so. Now, after our classes, I would appreciate it if you keep your questions that you may have, keep your questions short. And the reason being is because I have to pick up my children from daycare right after class. When we get done here at 5:15, my daycare closes at 6. It usually takes me about 20 minutes or so to pick up 2 kids. So if you have questions, I can answer them, but please make them short. I'd be more than happy to answer your questions, though, before class, preferably in my office because it takes me about 10 minutes to get everything set up here. Even though I don't have office hours, I usually am in my office right before class. So, any questions? Okay. Let's see what else. So project number 1, hopefully I'll get that out. I'll hopefully post it on Wednesday. It's pretty much written. It's just depending upon how far we get today, we'll make. I'll base that, or based upon how far we get today, I will decide if we're ready for project number 1 yet. Any other announcements? No, I don't think so. Good. Let's briefly talk about that day number 1 quiz. For some reason I didn't do this, but I did not post a message on the listserv saying that there's an answer key. I don't know if any of you by chance were poking around my website this weekend and came across the answer key, but there is an answer key on the test web page. You can download it from there. And this is what it looks like. Now everyone got 10 out of 10 points on the day number 1 quiz. And again, that will be part of your projects and quiz grade that we will keep going, adding to throughout the whole semester. And I do encourage you to read through the entire answer key because how you might approach the problem might be different from how I have approached the problem. And I want to point out a few different things regarding the answer key. And these are more, at least some of these are more format issues with the stuff that you hand in to me for projects. And I have to admit, I am a little bit picky on how you do stuff for projects, and my pickiness comes about through it makes it easier for me to grade and also for me to run your code. So let me find an example here. Okay, so like on part F here, I'm asking you to simulate some data and do some calculations. Now, when you copy and paste your code into a Word document, please first change the font to Courier. versus Arial or whatever font you're using. First of all, it helps differentiate that from just regular text. But most importantly is because your Courier font, each letter is equal spaced. And so if you have stuff that's like printed like in a kind of a table structure, depending upon what font you use, the table structure, the columns might not line up. And so that's why I always prefer Courier. If you take a look at most books that include stuff on R, you will see that they print the R code in a different font, and usually it's Courier. Okay, so one, remember, Courier font. Number two, always show your R code with output embedded inside of it. So don't just, let's say, run some code and only show me the very last line that has the numerical result. Show me all your R code that was used to generate some whatever answer you're generating with the output embedded inside it. So you'll notice here, this is my actual R code that I got from the R console window. You see some of my answers here throughout. And the reason why I want to see the answers embedded in here, because this will help me diagnose things that might have went wrong when you executed your code. That's why I like to see it that way. And lastly, now if I were to run some of this in R, let me actually just do this right here at the beginning of the demonstration. Notice how you see all these plus signs? And if I were to copy and paste all this into into Word, I would get those plus signs. I don't want to see plus signs. The reason being is because I will often copy and paste your code that's in your project into R to figure out maybe what went wrong or to verify that indeed that you did get the right answer. And I have to go through here and delete all these plus signs if I have to do that. So please help me out and do not put the plus signs or remove all the plus signs that are in your code. So those are just some format issues when you're actually doing a project and you are turning in some stuff with the project. The second thing I wanted to mention is to try to always use argument names inside of a function. So for example, some of you were doing stuff like this, matrix NA 2, 2, let's say, something like that. And that gives you a 2 by 2 matrix. Or let's say if I did 3 here. Instead, I strongly recommend that you actually put the argument names in here so you know, for example, that rows are listed before columns in the matrix call. That will help you avoid potential mistakes that might pop up. So it's always good to get in the habit of using the argument names, except for the most basic functions. Like if I want to find, suppose I have x, c1, 2, 3. If I want to find the mean of x, I just typically do that. I don't actually put x equal x to do that. So for the most basic functions, don't worry about. But for functions that are typically you're going to have, let's say, more than one argument in there, try to always put the argument names in there. So again, take a look at the answer key corresponding to our project. Quiz. Were there any questions about the day number 1 quiz? Okay. So let's continue in the notes then. We'll finish these notes up. We left off on page 124. So the stuff that we're doing right now is just to kind of review some small aspects regarding R to make sure that you understand it so that this will help you out in the rest of the semester. So in particular, we will be writing a lot of functions in this class. If you've had me for a class before, typically in those other classes, we really haven't written too many actual functions ourselves. In this class, we will. So it's important that you know more about writing functions than if for another class before. So, as all of you know from the day number 1 quiz, of course, the last line of code in a function is what's returned to the user. There's a variety of formats that you can use to return items to the user. You can use a list format, you can use a vector format. Depending upon the situation, use one or the other. You'll notice a number of you, I commented on that aspect in your day number 1 quiz. Typically, at the very last, you will either see list or you will see the C function that's used to return the items. Okay. Now, in the help for a function, let's say, for example, we look at the help for LM. LM is, in case you don't know, by chance, LM is used for fitting regression models. And in the help for LM, you'll see this ... Does anyone know what that ... means? Without looking at the notes. What this enables you to do is pass in additional arguments that are not necessarily listed here. Typically, these arguments are arguments that might be used for a call to another function that's inside of LM itself. So, for example, LM, if you actually look at the code, and we will shortly, calls another function called lm.fit that actually performs the numerical calculations. And there are other arguments in lm.fit that you can pass through LM itself through this ... here. So you can see, for example, in the help here, arguments, additional arguments. You pass to low-level regression fitting functions. So object names in the function line with an equal after are default values. And I think all of you got that in the day number 1 quiz. If we take a look at the help again for LM. So for example, by default, let's see now, contrast is equal to null. Model is equal to true, and so on. The arguments that you may have to specify are the ones that don't have anything after it, such as formula. Although sometimes you'll see stuff here like data, it's an optional data frame. So just because there's nothing after it, equal whatever, does not necessarily mean it is a required argument that you always have to specify. And lastly, you type the function name in the R console window. Guess what? What happens? You get the code. Yes, that's one of the beautiful aspects of R. R doesn't want to hide anything. It's completely open source. And so if you actually want to see the actual code of how stuff is done, there it is. Now, does this code look very readable to you? Yeah, there's a lot of stuff in there you're wondering, what is that for? How could you determine what match.call means? Or what this line's doing? How would you determine that?
Run it.
Run it, yeah. So what you can do is figure out in any kind of function, not just this one, but any kind of function that you see out there, copy all this code into, let's say, tin or whatever editor that you're using, and run it line by line by line. And that's how you can learn the R language itself and what certain things do. Of course, when you do that, though, you're always going to need to set what the argument names are. So you're going to need to set first, what is formula? What is X? What is Y? And so on. You need to actually set those values, and then you can run this line to see what is actually being done. Okay. So let's go to page 125 then. And what I have here is just a simple little example. Some of you have probably seen this data set before. This is my GPA data set. where we would like to use high school GPA to predict college GPA. We have a sample size of 20. I'm not going to go into the details of analysis. The purpose here is to understand certain aspects of how R is run. So the data set, gpa.xls, you can download it from your website. It's an Excel file. I use the RODBC package to read it in. If you've never seen the RODBC package before, there it is. We run this code and you can see how it works. I use the head function just to print off the first 6 observations. There's no need to print them all off. I use the LM function to actually estimate the model, where I say formula equal, here's my response variable, college GPA, my predictor variable or explanatory variable or independent variable is high school GPA. There it is right there, and I say data equal GPA. Put the results into mod.fit. Now, another way that I could have done this exact same thing is I could have said GPA $college, could have said GPA $HS, and remove the data argument. Data is not actually required. Then I use the summary function to summarize the fit that's inside the model. Summary is a generic function. Does anyone know what a generic function is? We'll talk about what generic functions mean in R. And then to see what's actually inside a mod.fit, I use the names function to see a list of the names of the items that are inside of it. And also, I should say as well, if I want to see the class of the object, I just say class mod.fit, and I get LM back. Okay. Now, let's see. So we already done 127. 128 is the actual code. So I copied and pasted this code from TIN. If you're not familiar with using TIN by chance, if you ever have some code in TIN and you want to preserve the actual color coding when you're copy and paste into Word, just highlight the section, edit, copy formatted to RTF. Come back over here, open up a new Word window, and there's everything color coded. Okay. So that's what I basically did, though, with the LM function. So we had just looked at the LM function inside of R. This is what it looks like here after everything is color-coded in TIN. I'm going to go down here. Okay. So remember, the last line inside of a function is what's returned to the user. In this case, something called Z is what's returned to the user. Well, where does Z come from? So, you can look throughout the code here, see where's Z coming from. And the main thing where it's coming from is right here. Actually, we'll go right here. Okay? There's a few places where Z is created, but this one will suffice. And we can see that Z comes about through using the lm.fit function. This is the function R that's doing the calculations. And it puts the results into Z. And if you actually look at the lm.fit function, so here's lm.fit. And then the important part right here, we see a dot call. This is actually calling out to a C program that's doing the calculations, the nitty-gritty matrix calculations. Why is it using a C program rather than program in like x prime x inverse x prime y into here? Well, it's because C programs are going to be faster than doing it inside of R. That's why. And in the end, just happens to be that Z, you have some information about Z right here. Okay. Let me just go back. So you see some other stuff that's put into Z. Notice you see these dollar signs after these Z $ call, Z $ term. So what's Z in terms of the type of R object? What kind of object is it, do you think? It's not a data frame. List. Okay. You remember what a list is. List is actually a data frame is a special case of a list. But the nice thing about a list is you don't have to have everything being the same length. It can be a variety of different formats. And so we can see that then a list is returned. And of course, to see the contents of a list, that's where I used names. So for example, you see call, you see terms there. Well, where did those come about? It came about right here. And you can go farther up in the code to see what's CL, what's MT. You can do that in there. Well, what's the class of an object? Or what's the class here? Notice the class is created right here. It's either MLM or LM. And for our example, it ends up being LM. So we're just simply doing a simple linear regression model. I'm not for sure what the MLM would be, to be honest. Yeah, I didn't pay attention to that before. But anyway, the thing is LM. So where does then, so that's where that came from. So I'll ask a very general question then is, well, what does the class of an object mean to us in R? Every object has a class. What does it mean? Why do we have classes?
So we can use it later.
Yeah, so we can use it later. Very good. How are we going to use it later?
All I know is I was running into a problem when I was doing an R thing. It said whatever function was can't use something that had a class that didn't match the class that I had. So.
Yeah, no, that's good. But we have to know, well, why? What are our classes? Why do we have classes in R? It's like one of the really, really big aspects of understanding how to use R.
I don't think the generic functions you're talking about and it's more specific.
Well, yeah. You're getting at it. You're getting at the answer. So every object in R has a class. This is why you often hear R referred to as an object-oriented language. Because depending upon the class of an object, or let me restate that. The class of an object determines how a particular function is going to react when it encounters that object. So, for example, summary. So when I did summary.fit, this is what I got. Just a summary of my regression model. But if I did instead summary GPA, look what I get instead. Something totally different. Why does that happen? Because the class of GPA is data.frame. The class of mod.fit is LM. So R is called an object-oriented language because a function is going to have different results depending upon the class. And this all comes down to then stuff called generic functions. Summary is a generic function. In fact, if I were to say help summary, one of the first things that's said here is summary is a generic function. The way that generic functions work is this. When I say summary mod.fit, the first thing that R is going to do is, let me raise that up too so it's easier for you to see. The first thing that R is going to do is look, what is the class of the object? Ah, it's LM. Then what happens is R then goes to another function called summary.lm. And that is what's actually executed. Let's look at the other example. So if I say summary GPA, which is the data frame that has the data in it, first thing it's going to do is look, what's the class? Data.frame. And so it's going to look, is there a summary.data.frame function out there? Yes, there is. And find it. Now, why do you think ours set up like this? Well, you know, it's would be kind of a pain to always remember. Summary.data.frame, summary.lm, summary.glm, summary.nls, summary.whatever, to do basically the same thing. Summaries. And in fact, if you look at other R functions, such as, you've all run into plot before. Plot is generic. Predict is generic. Residuals is generic, and so on. Because we often want to plot data or plot results from a model fit. We often want to do predictions for a model fit. It doesn't matter what kind of model it is, you still want to do predictions. So that's why R is set up this way, so that we have the same language that we can use, whatever kind of thing that we're doing. We can always use the same language, even though not necessarily the same resulting function is actually implemented. So functions like summary.data.frame, they are called method functions. So generic functions call method functions. Here's something that's not in the notes, and I wish I would have put it in the notes. And that is, suppose you want to see all the method functions associated with a particular class, such as LM. So I say methods class equal, quote, LM, end quote. Here are all the methods functions. So, for example, we were using before summary.lm. Let's look at another one. Let's see. Suppose I do ANOVA.lm. So if I said ANOVA mod.fit or ANOVA.lm mod.fit, I get exactly the same thing, which is, as you would expect, an analysis variance table. But in other applications, other than just simple linear regression like this, you might use ANOVA to do other stuff. I took my Stat 875 class category data analysis. You know the ANOVA function allows you to do likelihood ratio tests, for example. And lastly, suppose you wanted to see all the generic, let me just type this first, all the methods functions associated with a particular generic function. You see methods, generic.function equals summary, and look at all that. Because we want to, do summary of generalized linear models. We want to do summary of low-S models. We want to do summary of nonlinear models. We want to do summaries of, summary of linear models, summary of ECDFs, empirical distribution functions, and so on. That's why you see all those methods functions associated with this particular generic. Now, one of the most important things then to get out of this is, well, where do I look for help? Suppose I want to look for help resulting from using the summary function with the fit of a regression model. Do you look up the help for summary? No. You look up the help for summary.lm. That's what you look up. If you just look at the help for a generic function, it's not going to be very helpful because it needs to be very generic. To be specific, you have to look at the method function help. Okay, one last thing that I kind of skipped over here. Be real quick. This is on page 130. We will be writing a lot of functions in this form. This is a simple example. Let's say I want to find a trimmed mean. Someone tell me what trim mean is.
Values.
Chopped off. Yeah. So, let's say if I want a trim mean where I chop off the smallest and the largest value, for example. If you might hear about like a 25% trim mean. That would mean, let's say, the bottom 12.5% of your data and the top 12.5% of the data is chopped off, and you find the mean of the rest. Well, there happens to be an argument in the mean function that allows you to do trim means. But let's say I want to actually write one function overall to do the trim mean for some reason that allows you to pass in some additional arguments. So we often have a statistic called t in this class. And so if I want to say count.t, I can say function, I'm going to pass in my data, and we will frequently put another argument here called I. I stands for indices. Which data values do I want to find the statistic for? And then, maybe I might have another argument, trim. By default, trim is equal to 0. No trim mean at all, or no trim mean at all. Or I could change it to something else if I pass in a different value. Then I can say data2 gets what's in data, but I only want the particular observations that are specified in I. So if I have a sample size of 20, let's say, and if I say 1:20, that means 1, 2, 3, all the way up to 20. That means all the observations. Alternatively, I could say maybe I should be just, let's say, 1, 2, 3, and that's it. Then, last line, this is what's returned to the user, mean. What's in data 2, trim. So if I try it out, I calc.t, I get 2.5 with my, and y is actually my college GPAs. Sorry, I forgot to mention that. Now the reason why this is going to be so important here, this I here, is because remember what we learned earlier in this chapter with resampling. Sometimes you might not get 1, 2, 3 all the way to observation 25 in the resample. Maybe you get 2 of observation 1, and then observations 3 through 19. This provides you a way then to do the calculation quickly by only specifying the particular observations that appear in the resample. Okay. And I think that concludes chapter 1. Okay, let's do chapter 2. So on the schedule webpage, you see something called Notation Summary Sheet. Don't need to get that out, but I'm going to briefly mention it right here. This is what it looks like. So when I first taught the class in 2006, a common problem amongst my students were they were really having problems with the notation, understanding what means what. And when I was talking to another professor at Kansas State University who teaches this class as well, and I was talking about that. He said, "Yeah, my students just find this class really hard." And I was starting to think, well, maybe it's because of the notation, because the notation with the Bootstrap can get difficult to understand that why is the actual data or is y a resample? And to make things even a little bit more confusing is that sometimes, well, the book actually ends up using 2 different notations to mean exactly the same thing. Obviously, for people who are just learning something for the first time, that's not a good idea. Now, not surprisingly, when I was a student at Kansas State, and I took a readings course using this book. In case you haven't noticed, my book is on the back cover of the book as the person who reviewed the book. Take a look at your own, I guess. I was hoping all of you would take out your book and look, oh yeah, his name's there. Is my name there? Yeah. It says who reviewed the book, has the reviews. Yeah, okay. So my name's there. So actually, as my final exam for the readings class, because this book had just come out, was to write the book review. And then my advisor, who I took the class with, then he changed some stuff around, and that's why his name's listed first. Interesting though, the first time that they put our names on the back cover of it, they misspelled his last name. And so when we were at the joint statistical meetings, we actually went up to the book publisher and said, yeah, there's our name. Oh, you know, you misspelled such and such. And what do you know? The next time they printed the book, it was correct. Anyway, though, but when I took the readings class from my advisor, you know, I didn't really have problems with the notation because I already had some experience with Bootstrap before. And so that's why, you know, both of us were kind of surprised when we were teaching it in a regular classroom setting, you know, students were really having a hard time with that. And so that's what led me then in 2008 when I taught the course, is to construct this little notation summary sheet. At least in 2008, 2010, when I've taught the course since this has been created, I haven't had the same kinds of questions anymore. So I hope that this is the reason in terms of this explains the different notations and the equivalences between the different notations. So what I recommend that you do is, you know, you might want to bring this to class with you, and then if I'm talking about something it's not totally clear what I mean by T of F hat, well, you can look, oh, there's T of F hat. Oh, that's my statistic written as a statistical function. Okay, good. Or if you're doing the projects or reading the book, you have this all summarized here. So that's the last I will say of it. Talk about that unless there's any questions about it in the future. Got too many files open. Okay. So chapter 2, I think, is really the core chapter in the entire book. If you look at the schedule webpage, this is by far the chapter that we spend the most time on. If you can get through chapter 2, you'll be able to get through the rest of the course, simply put. Chapter 2 is broken into 2 parts. The first part kind of even talks about some of the stuff that we did in chapter 1. And I think maybe the more difficult ideas, there's some difficult maths. It's more keeping track of the notation here and understanding what's the difference between something called y and y star. It's the second part of chapter 2 that will draw on some really advanced math that you may have had before, and I'll have to probably help you some with some of that advanced math. So the first part of chapter 2 I think is easier than the second part. We shall see. Okay, so to begin with here, we spent some time in chapter 1 talking about why it's important to know what F is. And you know, typically in a real life example, you're not going to know what it is. And so what can we do? Well, you can estimate it with what we call F hat. One way to estimate it is with the empirical distribution function. Should be clear by now what the EDF is, just real briefly. If I want to evaluate the EDF at a particular value of y in a non-mathematical way, you can say the number of the y sub j's that are less than or equal to y divided by, in other words, it's a proportion. How many of your observations are less than the value of y that you're evaluating this function at? We could also alternatively define this a little bit more succinctly by using an indicator function, as we did last time. Here. What the book uses instead is this function h. It's called a Heaviside Function. And it's basically the same as an indicator function, but it's just defined in a little bit of a different way. In terms of if y minus yj is greater than or equal to 0, in other words, y is greater than or equal to y sub j, my function h is equal to 1. Otherwise, it's 0. So you can see how it's just basically an indicator function, just written a little bit differently. Just want to point it out to you because this is what the book uses rather than indicator functions. So, you know, real briefly here, just to make sure we're following. You know, let's say I have a simple sample, y1 is 1, y2 is 5, y3 is 2. Then define f hat, evaluated at maybe like 2.5. I could have picked a different number if I wanted, so I just said 2.5. Then with this h function, then, we look at, is 2.5 minus 1 greater than or equal to 0? Yes, it is, so I have a 1 here. Is 2.5 minus 5 greater than or equal to 0? No, it's not. So I have a 0 here, and 2.5 minus 2 is greater than or equal to 0, so we have a 1 there, so that f hat of 2.5 is 2/3. 2 out of 3 of the observations are less than or equal to 2.5. And so essentially what the EDF does, it puts probabilities of 1 over n on every observed value. That's it. And we can kind of think of f hat then as kind of a fitted model, a non-parametric way to fit your model in terms of if you think of a model as a CDF. And we're going to use f hat for the non-parametric bootstrap. We're also going to spend some time talking about the parametric bootstrap. At least I don't think I've mentioned that yet in Chapter 1. Did anybody go to today's seminar? Okay, we had one. Today's seminar, Muhammad Yassin did his dissertation defense. And what he did was he used the parametric bootstrap, where he had a distribution of a statistic that was kind of messy. And he said, okay, I'm not going to worry about this asymptotic distribution. How about we just bootstrap it? And so he used the parametric bootstrap to solve his problem. Anyway, so, well, what's a parametric bootstrap? Well, in this particular case, you're going to say that f has a particular distribution. Normal, let's say, theta 1. Well, theta is just some mean parameter. Then what's f hat? Simply, theta hat 1. And so how do you take your resamples? Well, sample from a normal distribution with mean theta hat and a variance of 1. That's all you do. If you didn't know the variance, well, estimate that too. Plug it in there for the normal distribution, estimate and resample from that. That is the parametric bootstrap. We'll be spending a lot of time on that shortly. Okay. So we need to talk about something called statistical functionals, or statistical functions. Has anybody heard of statistical functions before? I'm not talking about functions in R. Anybody heard of statistical functions like in a, I don't know, some of you take semi-parametric class that Dong taught? Did he talk about functionals at all? Okay. Statistical functionals are often used in robust statistics. Robust statistics, an area of statistics where, like for example, for a trim mean, that's a more robust measure of centrality than just a regular old mean. Meaning it's not as affected by the by outliers as the mean would be. And so they're used a lot in robust statistics. We're just going to use them a little bit here to help you see what the bootstrap is trying to do. And also we'll come back to what statistical functions are in section, I think, 2.7, when we have to define something called an influence function and the non-parametric delta method. Okay. So a parameter is basically a numerical summary measure of a population. It's a function of your population. So why don't we just represent that mathematically then as a function of your population? If we let f denote basically our population, the way that we see it through a distribution, we can then define our parameter of interest, let's say theta, as t of f. That's a statistical function. Again, to emphasize that it's a function of the population. Now for a statistic that's going to estimate this parameter, again, a statistic is a numerical summary measure of the sample, or it's a function of your sample. Well, what's representing our sample? F hat. So what we can say is our statistic of interest, let's just call it T for short, can be represented as T of F hat. So what we have here is that T estimates theta, or equivalently, in terms of writing everything as a statistical function, T of F hat estimates T of F. And what you're going to see shortly is that this gives us a nice mathematical way to define, to say that I have this parameter, what's the statistic that estimates it? But before we do that, we need to talk about a Stieltjes integral. So all of you had Calc 1 through Calc 3, and you talked about Riemann integrals. But some of you, I bet, have not seen Stieltjes integrals before. I assume that you've taken Stat 8, 9, 80, you've talked about something that's closely related, a Lebesgue integral. Yeah. A Stieltjes integral is going to be really, really simple for us, okay? It's simply just a way for us to basically use the little integral symbol with respect to a continuous distribution or a discrete distribution. That's it. That's all it's going to mean for us. So if I want to find the integral of y df of y, what that just means that if f is a continuous distribution, take the integral of y times f of y dy. That's all. So that'd be like your expected value of y. That's all it means. If, though, instead, f of y was a discrete distribution, then what that integral basically means is this. Take the sum over all your possible values of y times the probability y is equal to y sub j. That's it. Now you can imagine that, let's say if we have some kind of distribution that's both kind of continuous, it has some discrete points in it, you can see how this notation can be kind of helpful as well. At least for us, though, it's either going to be continuous or just discrete. If you want to know more about it, there's some references. Okay. So now that we have that defined, let's talk about some examples. Simple examples. Suppose theta is the expected value of y. So written in terms of a statistical function, we can say t of f, or, and again, this is the notation that the book is, you have this means this means this, and this means this, or in other words, the expected value of y given f. That given f there is not necessarily a conditional probability, is to emphasize the fact that this is the distribution of my random variable. My sampling is coming from f. We're in terms of the Stieltjes integral y df of y. Okay? We could also define a variance like this as well. Suppose theta is my variance, so you can say theta is t of f. Okay, it's a function of your population. Then we have the expected value of y squared given f, minus expected value of y given f under the squared, and we can write that in terms of two Stieltjes integrals. Okay. Now, why are we doing this? The reason being is because, again, in real-life applications, you're not going to know what f is. So what should you do? Replace f with f hat. And so this notation helps us see that replacement actually being done. So we do what's used, or what Efron, I don't know, I would say probably Efron came up with this name. I could be wrong, but this is what I first read about with some of his papers. We're going to use what's called the plug-in principle. So if I want to estimate a parameter, I plug in f hat for f and see what the estimate comes out to be. So in terms of estimating expected value of y given f, well, let's let our statistic be t. In other words, t of f hat, or expected value of y given f hat, is equal to now the Stieltjes integral of y df hat of y. Of course, f hat, though, will be discrete. Also, what this is basically saying is that y, how my data is coming about, you can say it's coming from the f hat. Suppose I want to look at the variance then. So t is equal to t of f hat, and I just simply plug in f hat, wherever you see an f, and this is what my variance would look like. Now, if f hat is the EDF, so if we're going completely non-parametric here, on your own, think about what would happen in a parametric case. We'll kind of talk about that shortly too. We'll just talk about non-parametric case here, where f hat is actually the EDF. Look what happens. By plugging in f hat, that means now that this still just integral is just simply the sum from j equal 1 to n, y sub j, probability y is equal to yj. But remember, EDF basically puts a probability of 1 over n on all your sampled values. So, this is 1 over n. I can factor that out. Look what I'm left with, y bar. So what this plug-in principle and what this statistical function allows you to do, it finds it allows you to have a convenient way to come up with an estimator. You're substituting f hat for f. Let's look at the variance. So what that ends up happening is that, of course, I'm going to have for this integral of y squared, I have a probability of 1 over n for every single item, but also I'm going to have a y squared there instead of just a y. And I have what I have had before for the integral of y. Go through the math, and you get what I like to say is the usual biased estimator for variance. So that you don't divide by n minus 1, you divide by n. So there's a way to estimate your variance. It's not perfect, obviously. We know that. It's not unbiased. But is f n's large? Of course. It's not going to matter. Well, you can also write other more fun quantities, depending upon your feelings on this. Other quantities as statistical functions too. So, for example, your median. What's the median? Well, 50% of your data, 50% of your values in your population should be lower than this value, 50% above. In other words, T of f is equal to the inverse CDF evaluated at 0.5. Excuse me. Well, then what would be then the statistic then for T of f hat? Well, just put a hat on top of the f. Is it hot in here?
There's a heat radiating out the windows.
Do we maybe at least close that window? Close both of the windows, the one in the back too? I'll open up the door too. Thank you. So what this is saying then is, well, what do you choose as the median? Well, you look at your sample values and look at the one that's going to give you a probability of 0.5 to the left of it, or 50% of them will be to the left of it. And you have to be very careful with respect to this, what you mean by that, especially if you have, let's say, an odd number of observations. And there's various definitions then that you have to specify with regards to that, and that's why I did this here, where you have a greater than or equal to there. And notice that this result then might give you a different value than, I guess it was the even number value. It might give you a different result than what you would get in like Stat 218 if you're teaching a median in that kind of setting. You can also think of a sampling distribution for a statistic of interest T as a statistical function as well. Again, remember how important it is for us to get this sampling distribution. That's one of the big reasons why we use the bootstrap. Get that sampling distribution. And so you can think of the sampling distribution of a statistic T as G of T given F. That's the true distribution. Then what you can do is simply plug in an f hat there to get an estimate then of that true sampling distribution. How about the bias? Well, typically we think of the bias of the statistic as the expected value of the statistic given the distribution for the y's, let's say, minus the actual parameter itself. Well, notice how I define this in terms of a statistical function. Well, how do I estimate the bias then? Because of course, we're never going to know what theta is. And are you sure you know what f is when you calculate that expected value? Well, how can we estimate that? Plug in f hat. And we'll look at examples of doing that shortly. Okay. So lastly, to conclude this small section, a little change in notation. I will always say that y is distributed f, and then t has a distribution g, where t is your statistic, a random variable. This is the sampling distribution. Now, whenever I deal with f hat and g hat, I'm going to use stars. Y stars distributed f hat, t stars distributed g hat. I believe we looked at that y star notation and t star notation in chapter 1. This is just helpful to keep track of what everything means. Okay. So, page 2.7. We're going to talk about the parametric bootstrap first, rather than the non-parametric bootstrap. Because the parametric bootstrap helps you see how the bootstrap world works in a setting that you're more familiar with, and that is when you say y is distributed exponential, or y is distributed normal. It's easy then to figure out, okay, y star will be distributed some distribution. So we're going to begin with the parametric bootstrap. And this is the world as you knew it before you came into this class. And that is, if you wanted to be completely parametric, you would have said y is distributed f, where f might depend upon certain parameters. We'll just call those parameters psi. Psi could be a vector of parameters. It could be just one parameter itself. And this f then generated your sample y1 through yn. Okay. Now, using the sample in f, we can use particular statistical techniques, such as you learned in Stat 883, to estimate what these parameters psi would be based upon your sample. Maybe maximum likelihood estimation, and so you would have then estimate psi hat. Also, based upon what the distribution of f is in your sample, you would be able to derive mathematically what the sampling distribution is for g, or maybe use Monte Carlo simulation to estimate it as well. Now, though, in the bootstrap world, we add the following. We're going to use an estimate of f. We're going to say that we know what f is, or at least we know its form. Maybe normal mu sigma squared. Maybe we plotted the data and it seemed to make sense. It was a reasonable approximation. Then, to get f hat then, well, we just plug in our parameter estimates. That's it. So the bootstrap then uses, let's say, f hat, or you could say f of psi hat. So if I had f being normal mu sigma squared, then f hat would simply be normal mu hat sigma hat squared. What do you use for mu hat? What do you use for sigma hat squared? Well, it depends upon what you want. You probably would use the mean for mu hat. Use probably the unbiased estimator for sigma hat squared. Because you know that that's going to end up being better in the end. So might as well take advantage of that knowledge. Then what we can do, once we have that, then we can define a random variable y star that is distributed f hat. And again, this f hat could be something like that there. And depending upon the statistic that we have of interest, we may be able to simply derive then what the distribution is for the statistic of interest t star. And do some other calculations that in the end will help us learn more about theta. Or I should say, theta, the parameter that we're interested in. The distribution of t star is again going to be g hat. Okay. Let's see here. Sorry, I've lost my train of thought of where I was going with this. So we can use this setup then to find expected values. So for example, if expected value of y given f was mu, then we could say, well, expected value of y star given f hat is equal to mu hat. Also, we can look at expectations for t and t star as well. Let's take a look at an example. Suppose t was the sample mean, which you could say y bar, but as you will see in this notation, it's easier just to call it always t. And this is in that normal distribution example. So we know then that the distribution of t is mu sigma squared divided by n. Nothing new there. So you can say that the expected value of t star given f hat is, in other words, just mu hat, for example. Well, what will be g hat then? So this is g. G hat then, well, again, just plug in, put the hats on top of the parameters. Okay? This is then your estimate for g. Now you might be wondering again, why are we doing this? We know what g is. Think of a setting where the distribution of t would be difficult to find. This is why we're doing this. Think of it with respect to that aspect. Suppose t instead was the unbiased sample estimate, unbiased sample variance, s squared. In your stat, probably 883 class, you've done this proof. Expected value of t given f is equal to sigma squared, right? Again, your data is underlying normal. T star, you could call s star squared, or you can see this is where the notation gets kind of weird. S squared star. That's why, again, we typically work with just t. Well, what will be s squared star? Well, again, just your sample variance now of your y stars. What's the expected value of t star given f hat? Little s squared. Your observed sample mean. I'm sorry, observed sample variance. Again, think about y. Perhaps I'm repeating myself too much, but that's okay. y1 through yn is distributed normal. y1 star through yn star is distributed normal as well. So just using basic concepts of what you learned in 882 and 83, we have normal random variables here. What's the expected value of this sample variance? Well, it's the variance for the actual distribution. That's it. Also, you learn in 882 or 883, n minus 1 s squared divided by sigma squared is chi squared n minus 1. Hopefully that looks familiar, because we're again having an underlying normal distribution. What's the distribution of s squared? Ever talk about that in 882 or 83? Well, you know the relationship between a chi-squared and a gamma. Chi-squared is a special case of a gamma. So you can go through the derivations, and s squared is gamma. First parameter, n minus 1 divided by 2. Second parameter, 2 sigma squared, n minus 1. Then what's the distribution of g hat itself? Again, just replace the sigma squared with the observed variance. That's it. Okay. Seem to be going fast here, at least I think I am. So if there's any questions, please feel free to stop me. Notation. This is what I was mentioning earlier. The book will use two different forms of notation meaning exactly the same thing. Expected value y star given f hat, which is what we've been talking about here, will be equivalently represented expected value star y star. Why? Less keystrokes. That's it. So please be aware that that notation's used, and you need to be comfortable with both. So how can we do some of this stuff through Monte Carlo simulation? Well, again, typically this is how you would use the parametric bootstrap when you can't derive this stuff easily. We're looking at cases where you can derive, so we have something to compare to. So in a Monte Carlo simulation setting, suppose I want to estimate, or I want to get expected value of t star given f hat. So I want to estimate it essentially using, let's say, capital R resamples. Then this is what we're doing essentially. This is again the world before the bootstrap. Then with the bootstrap now, we know what f hat is. And if we know what f hat is, we have ways to take samples from f hat. So we get sample 1. Okay, let's say y11 star down to y1n star. Calculate your statistic of interest t1 star. Do that all the way down to the rth resample. What these t stars then will give you is a way to look at the estimate of g hat. Since this is based upon R resamples, if you want to be more precise, you can call it g hat capital R. We did this kind of stuff in a non-parametric setting already in Chapter 1. So, since I have this distribution then, if I want to then estimate the expected value of t star given f hat, I just simply use 1 over R times the sum TR star. That's it. And we know by the law of large numbers that this guy is going to approach the expected value of t star given f hat. And essentially, what this is trying to do is estimate this. Okay. So let's take a look at a numerical example. Or I guess actually let me mention this too. We were talking earlier about the bias. Expected value of t given f minus t of f. And this is just, let's say, theta. Well, how can we estimate it? Well, you can estimate it like this. Expected value of t star given f hat minus t of f hat. This is your observed value of t. We know that. How do we get this? Right there. Estimate with that. Now we have an estimate of bias. Okay. So let's talk about how we can do some of this stuff in R. I don't think that we're going to be able to finish this example. Well, we just ended there. Are there any questions? Okay, that's it for today.